In this video, I would like to summarize a bit what we know about data types so far in Haskell. Data types are constructed using this, not constructed, defined using this data construct. And it is actually a rather versatile construct that can define data types of various different shapes. And this slide summarizes the general shape a bit. So we always start with the data keyword. We always introduce the name of the new data type, which has to start with an uppercase letter. And then data types can be parameterized, so there can be an arbitrary number of parameters. All these are taking the shape of type variables here, which have to start with lowercase letters. And then we can give a choice of possibly many constructors, so-called data constructors. And they all start with uppercase letters. And the data constructors are what we can use on the right-hand side of definitions, right, and expressions to construct values of the data, but they're also what we can use on the left-hand side of definitions in order to pattern match on the various different shapes of this data. And constructors can have arguments as well. They don't have to have arguments, but they can have arguments. And if they have arguments, then they're listed in this data type declaration syntax after the constructor as a sequence, as a space-separated sequence of the types of the constructor arguments. And it's perhaps a little bit confusing that the first item here, even though the types also typically start with uppercase letters, right, the concrete types that we're giving, that the first argument, the first position here is defining a constructor. So that is something that lives on the expression level of the Haskell language. And then the rest of the items that appear afterwards are the names of types that live on the type level of the Haskell language. But all the data type definitions that we have been seeing so far fit into this shape. Let's actually define another data type that exploits this general shape. And let's define binary trees with labels or elements in the leaves only. So this tree type is a data type that I'm defining. This is the name of the data type now. This is my one parameter. And now I'm going to give two constructors. The first is that of a leaf, and a leaf is having an argument, is containing one element of type A. And the second is that of a node, and the node has two arguments, namely it has a left subtree and a right subtree. And here we see this pattern that I've just been describing on the other slide, where, for example, in the case of node, we have three things appearing in sequence, but the first after the vertical bar here is the constructor name, and the constructor name after reloading is something that we can use as a function to construct a new tree, or use as a pattern in order to match on a particular tree and extract its components, in this case its left and its right subtree. Right, and the other items that appear afterwards are the types of the arguments of this constructor. So because we wrote tree A and tree A here twice, that is the reason that the type of node now says tree A to tree A to tree A, right? The result type is always going to be the type that we're just defining. That's why this tree A is here. But the argument types, these two, they come exactly from these two arguments. If I had said, look, a node has only one subtree, then the type of node would change so that it takes only one subtree as an argument in order to form a new tree. But we want two in this case. Right? I often Right, data declarations align somewhat like this. The layout here is relatively flexible. The only point is that all the lines that are still part of the data declaration, they have to be indented further than the original data declaration. Right. It's useful to derive show, so the deriving construct, if you like, is also part of a data declaration. If you want to derive type classes for a data type, it has to be put directly at the end of the data declaration, and then you have to list all the type classes. If you want to derive multiple type classes, we actually have to put them in parentheses. We are going to talk about type classes more in one of the next videos. So this now allows us to define values of this tree type, and this is a good example of a general data type definition, because in general data type definitions are always kind of tree-shaped. The choice between the different constructors gives us an option of defining different kinds of nodes, right, that have different branching degrees or different subcomponents, and the fact that the data type definition can be recursive gives us these classical tree shapes. So, how can one visualize something like this? So we can give an example tree here. Let's give a tree of integers. Just use a simple tree. So we can form a tree using the node constructor, and then say something like leaf 2, leaf 3. So now we have a single node that has two subtrees. The left subtree is just a leaf with a 2 in it, and the right subtree is just a leaf with a 3 in it. So we can try to visualize this. Let me see if this succeeds. So you can think of this as the node just being some sort of blob, right? And then you have a left subtree and a right subtree. Sorry, let's start once more. A node, oops. And then we have a 2 to the left and a 3 to the right. Right. We could also imagine doing a slightly larger tree where we have a node and then another node and then let's say a 4 here and a 5 here and then a 6 here. How would we do that one? Well, we can do another example tree. Let's call it example tree 2, which is another tree of ints. Now we also start with a node. That is this topmost node. Sorry, I forgot the 2 here. That is this topmost node here, right? And then to the left, I have a subtree that is more or less in the shape of our example tree 2, but it has different numbers in the elements. So the left subtree, let's put it on a new line, has the shape node of leaf 4 and leaf 5. And then the right subtree is just a leaf with a 6 in it. And at this point it type checks, right? So in this style you can draw arbitrarily large trees, and of course you can change your data type definition if you want to have a different kind of tree. If you would want every node to contain a number as well, let's say, then you would have to change the node constructor to hold an element of A additionally. If you would want the tree to always have 3 sub-branches, then you would change the node constructor to have 3 subtrees. If you want to have the tree to have a flexible number of subtrees in every node, then you could change the node constructor to contain a list of subtrees, for example. right? So there is quite a bit of flexibility. But in general, the data type construct always gives you these kind of tree structures. Even lists, if you look at them, are effectively tree structures. Only that they are very degenerated tree structures that only grow to one side. But if you remember, we had defined the list data type, or we had seen that the list data type can be thought of as being defined using this syntax where the first constructor is the empty list and the second constructor is cons. So cons is some kind of node. So you can think of a list that is, let's say, defined as 1, 2, 3. Right? That is really, as we know, syntactic sugar for 1, cons 2, cons 3, cons the empty list. These two lists are the same. So we could think of the cons as some kind of node. Let's write it as a colon here. And then as its left subtree, right, it just has the 1 in this case. And then as its right subtree, it has another cons. And that as its left subtree has the 2. And as its right subtree, it has another cons. And that as its left subtree has a 3. And as its right subtree has, in this case, the empty list. So in this way, you can look at even a list as some kind of tree structure, only that it's not ever going to be a balanced tree. It's always going to be a sort of right-leaning tree where the left branches are always just containing the single elements that are stored in the list, and then the right branches are containing the sublist. Nevertheless, that is a good way to visualize this. All right. There are interesting sub-cases of data types that are being allowed by this general syntax. The general syntax, again, allows us to parameterize data types. It allows us to give multiple constructors. It allows us to give arguments to each of the constructors. And it allows us to use recursion. All these things are allowed. But we have seen things that fall into certain special cases, such as one of the very first data types that we had seen was this choice data type, where we had rock or paper or scissors. Right? This data type is not parameterized. It has several constructors, but none of these constructors have any arguments, and therefore, in particular, it's also not recursive. So this is an often used subclass of data types, and these sorts of data types that have several constructors, but none of them have any arguments, they're usually referred to as enumeration types. So you just enumerate a number of possible values of that data type. And we have seen other examples of this as well. In particular, the Boolean data type. I've seen that. That is just having false and true as option. That's another enumeration type. Right. But you could also imagine that you define a data type for weekdays, where you have all the different choices of weekdays: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. You have quite a number of options. And another common special case is that you have data types that have just a single constructor but multiple components. And that's what pairs or tuples in general fall under, but also all sorts of domain-specific groupings of information. So, for example, if you have a user in your system, you may say, well, a user is always constructed using a constructor that you could call make user, or you could also call it user. As we have seen, you can reuse the type name as a constructor name. that is allowed in Haskell. And then you can say, oh, perhaps a user has an identification number that is an integer, and perhaps a user has a name, a user name that is a string, and perhaps a user has also an email address, which we'll get to that, but for the time being, let's say is another string. Right, and so we have three things that we group together: this user identity or identifier, the user name, and the email address. And so we have three things that we group together specifically for a user, and and we call them together. We call them this triple of information. We call this a user, and this is better than just using a triple, right? It's better than using something of type int string, because at least it conveys the meaning. At least it conveys a little bit of meaning of what these three pieces of information are for. Right? It's still not ideal because we have one int and two strings, and there is still a lot of imagination being needed. But together with a bit of documentation, at least. That's fine, and we can now, at least in a type signature, mention that we're expecting a user, and it's relatively clear that this information stored in there is about a user. We can make this better in several ways. One way is a syntactic construct that we haven't yet seen, and that is a record notation. So rather than just having these three positions here being unnamed, we could give them names, these components names. So we introduce this by using a curly brace, and then we give a name to this field. And it is relatively common in Haskell to prefix record field names with some abbreviation of their type that has to do with certain limitations of the record system in Haskell. There are some language extensions that work around this that are also becoming more and more used, but for the time being I'm going to follow this classic practice and will prefix every field here with a lowercase u. So I'll have uid for the identifier, and then uname for the name, and then uemail for the email address. Okay, so this defines now a record type with three components, and if you compare this to the original type that we had, well, let's actually keep that one with the user prime constructor. You can see that both these data types have a single constructor, and both these data types have three components, three arguments of the single constructor, one of type int and one of type string and one of type string. And in fact, they behave almost completely the same. So if you look at what is the type of user prime, that is now the one that does not use record syntax. You get int to string to user prime. If you look what is the type of user that is using record syntax, you get exactly the same, int to string to user. So in particular, if you want to build a concrete user, I can say I'm the user with the ID 42, and my name is Andres, and my email address is andres@welltype.com. I can do this, and I can bind this to a name. Let's call it lowercase Andres, and then I can ask what is the type of Andres, and that is the type user, has the type user. And similarly, I could have defined something of this type user prime in exactly the same way. So I'm not forced to use the record syntax, but I can now also do this. I could alternatively have constructed Andres not using this syntax, but I could have used this syntax, uid equals 42, uname equals Andres, and uemail equals Andres@welltype.com. And that means the same thing. So also, if I'm deriving the show instance, and that is something that we have been using for our own data types already, you'll see that record syntax leads to data types being printed in like using this record syntax. So even if I define Andres like this, right? If I now show the result, it is using this record syntax in order to show the value back to me. So these record field names, they're used for informative purposes. They can also be used to extract components. So if I want to get the username out of Andres, I can just use uname as a function. Right? There is no dot selection syntax. That means something different by default in Haskell. This is usually interpreted as function composition. There are now language extensions that are just being proposed and becoming more popular that allow this kind of dot-based field selection in Haskell. But by default, if you do not have anything like this enabled, and in the current version of the compiler, you select from a record using this function notation, UID of Andres is 42. So you simply use these extractors or these record field labels, you can use them as a function. There are a couple of more things that you can do with record syntax, but I don't want to go into too much detail here, just so that you have seen this at least once. So this is another common special case, right? And data types that have just a single constructor but group multiple things. I tend to generally call them record types, regardless of whether they use record syntax or not. But some people would also perhaps call the first one just a product type. Products, like you can define some sort of algebraic notion between types, and in certain ways, the choice between different constructors behaves like addition, and combining multiple arguments in a sequence behaves like multiplication. So that's why some people are talking about a type that just groups different things together as a product type as well. And perhaps you'll hear enumeration types being called sum types from time to time as well. Although I think sum types, the notion of sum types is in general also more widely used to any data type that has more than one constructor, that offers a choice at all. Okay, so there are a few more things that I want to say. So one issue that I've already mentioned is that it's not ideal, even now with the record field names, to sort of use an email, if you have an email address, to just use string for that. Perhaps it's not even ideal to use, if you have a form of user ID, to use int for that. Because you have many different ints in your program and many different strings, many different kinds of strings, and not all of them are supposed to support the same operation. So in general, it makes sense to add two integers and to compute their sum. But for user IDs, it probably does not make sense. If one user has the user ID 17 and another user has the user ID 22, then what sense does it make to add 17 to 22? That's probably something you simply never want to do with user IDs. Right? So you probably want to prevent user IDs from being added, and you may want to prevent other operations from being done as well. And the fact that you're using an integer in order to represent user IDs is more of an implementation detail. So what is useful from time to time is to define a new data type that is yet, in a way, a new special case that has a single constructor and a single argument. So you wrap an integer, which is a user ID, in a new constructor called user ID and a new type called user ID. And now integers and user IDs are different from each other. Right? And in particular, as we have been briefly discussing before, if you define a new data type, it starts out without any operations. So you can pattern match in order to get the int out if I really want to. But now if I have a user ID 42, let's do and a user ID 21, right? And I cannot just start adding them, not accidentally at least. Oops, why did I not save here? Okay, if I now try to do UID1 plus UID2, I will get a failure because the plus operation requires an instance of the num class, and we'll talk about the num class later, but it is nevertheless the case that we don't have any instances for a new data type. It is fresh, it does not come with any operations, so it is yes, nicely prevented that we do all sorts of accidental operations. If we still want to be able to show user IDs, we can say deriving show, right? But as long as we don't derive or define any other operations, we're pretty safe. And additionally, if we now write user ID as a type here or even here, we make it much clearer what this integer is in all circumstances. Even if we then pass it on to another function, if the type says user ID arrow something else, it's much more informative to the reader than if it says int arrow something else. And similarly, we could have a data type for email addresses, a specific data type for email addresses that would work according to the same principle. Because again, email addresses may be represented using strings, but first of all, not all strings are valid email addresses. But also certain operations that are available on strings simply do not make sense on email addresses. You probably never want to do them. You probably don't want to append email addresses to each other, because if you append two email addresses, you do not necessarily have a valid email address. You probably never want to reverse an email address or take a prefix or a postfix of it, or if you want to take a prefix of it, you only want to take, say, everything up to the @ symbol, right? Like a specific kind of prefix. So you may want to support different operations, and again, you can do this wrapping up of a single field in a single constructor trick in order to give yourself a new data type that leaves you in control as to what operations you want to export. You can explicitly convert between the original data type and the new data type. How can you explicitly convert? Well, in one direction, you can just apply the constructor, right? In order to create an email address from a string, you can apply the constructor. In the other direction, you can pattern match. Right? I can pattern match on something of type email in order to get the string out. Or I could use record syntax here as well. Something like get email to get the email out. Then I have a function get email, which extracts the one component from the data type. Okay. For this special case, there is also another Haskell language construct, and that is called newtype. And I don't want to go too much into the differences between newtype and data. The main reason newtype is there is for efficiency. So you can imagine that, or you can think about this in such a way that creating a new data type always introduces one layer of indirection. So it essentially always at least introduces one pointer. So even if you wrap up an integer in this user ID data type with one constructor, you essentially get one additional pointer until you actually find your integer. If you want to prevent that, if you want to have the guarantee that the runtime representation of a user ID is exactly the same as the runtime representation as an integer, you can use this newtype construct. It otherwise behaves almost exactly the same as the data construct, but it is restricted to a situation like this, where you have a single constructor with a single argument. You can only use it in a situation like this. If I now say, oh no, it would be good to have a user ID represented as 2 integers, I would get an error message, and that says something. A constructor of a new type must have exactly 1 field, but user ID has 2. Or if I would say, oh, well, no, a user ID can be either an integer user ID or a string-based user ID, which is using a string, then again, I would get an error message that says a new type must have exactly 1 constructor, but user ID has 2. So in any of these other cases, I would have to go back to data types. But if you are in this special case that you're wrapping a single type in a constructor and make it a new data type, then you can use newtype instead. And then many people are using newtype instead because it is slightly more efficient. There is a third construct that can be used to do something with types, and that construct is called type. So not new type, but just plain type. And that's a bit different. Type is being used to introduce so-called type synonyms, and we have seen one prominent example of this before, and that is that of string. So here we see the definition of a type synonym. So you write something like this, just like this. We can do a similar type synonym like for strings. We could say we have an int list type synonym, which we define to be an abbreviation for lists of integers. But where data types and also new types always introduce a new data type into the system that is different from any existing data type that we have seen so far, type synonyms just give a new name to an already existing data type, but they don't make a distinction. These names are interchangeable. So string and list of characters can be used interchangeably in Haskell. I could just replace this string here with list of characters and nothing would change. All my program would be guaranteed to still work, right? So string and list of characters are interchangeable because they're defined to be synonyms. Similarly, now with int list, I can say my list 1, 2, 3 is a list of ints, right? But I can also say it's an int list. Right? You can also use type synonyms to convey extra meaning about certain components. So for example, if this is a username, you could say, rather than defining a completely new data type for it, I at least want to have a type synonym that this string is being intended to be a username. So you can define a type synonym for it. And then we could change this here as well. Right, but there is a drastic difference because, again, here what we are expecting is just a string. Any string will do. It can be a string that has been defined in a completely different context. String and username are interchangeable types. Here, email, the way we defined it, is not a string. Email is a completely different data type. It can, internally, it contains a string, but we have to somehow turn it into the type email before we can use it in this position. So there is a drastic difference here. Type synonyms can be useful in some places for conveying additional information, but they can also be confusing because they, as I say, they are transparent, right? I mean, things can just be used interchangeably, and they can make something look foreign, unknown, without the necessity to, right? I mean, everybody knows what a string is, but if you see username, at first you won't know what it is, right? And then you're looking for the definition, or you may assume that it's a completely different data type, and later you discover, oh, it would have just been a string, right? So use these things with care. Also, it's perhaps confusing that type and new type, they sound very similar, right? But they are doing completely different things. New type is actually much closer to data in the way it behaves. right? It's a sort of restricted form of the data construct, whereas type is, in its behavior, completely different. Okay, I think that is enough as an overview of like how the different type definition constructs in the Haskell language work. I think the data construct is by far the one that you will use the most, and that we'll also use the most in the rest of this course.